We're surrounded by stuff, right? Our chairs, the water we drink, even the air we're breathing. We call all of it matter. But have you ever stopped to think about what it really is? Turns out the world around us is hiding some pretty wild secrets in plain sight. And today, we're going to uncover them. Okay, so think about this for a second. Picture a glass of water, filled right to the very brim. Now, you take a spoonful of salt, stir it in, and poof, it just vanishes. But here's the crazy part. The water doesn't overflow, not a single drop. So, where in the world did that salt go? This little kitchen puzzle, believe it or not, is the key to understanding, well, everything. All right, let's dive into this disappearing salt mystery. What looks like a simple magic trick is actually pure science, and it's about to show us the very first fundamental truth about the world. Seriously, you can try this at home. It's super easy. Just mark the water level on a glass, stir in some salt, and watch. The salt just disappears. But the water level, it stays exactly the same. It's like the salt took up zero space. So what's going on here? Where did it go? And here's the big reveal. Matter, it isn't this solid, continuous thing we imagine it to be. Nope, it's actually made of tiny, tiny particles with empty spaces between them. So when you dissolve salt in water, the little salt particles aren't pushing the water particles out of the way. They're just slotting themselves right into those empty gaps. The salt didn't vanish, it just found some empty real estate that was there all along. Okay, so we've established that everything is made of these tiny particles with gaps in between. That naturally leads to the next questions, right? What exactly are these little building blocks like? And just how tiny are we talking? I mean, it's one thing to say particles are small, but really, truly grasping the scale, it's almost impossible to wrap your head around. But don't worry, a really cool little experiment can give us a peek into this incredible invisible world. Okay, check this out. You start with just 2 or 3 tiny purple crystals. You dissolve them in some water, and boom, the whole thing turns a deep, vibrant purple. Now you take just a little bit of that purple water and add it to a new container of clear water. Then you do it again, and again, and again. Even after you've diluted it so many times that you'd think there's nothing left of the original, the water is still faintly purple. That's insane. It means those first few little crystals must have been packed with millions, maybe billions of tiny purple particles, spreading out through all that water. Yeah, this quote just nails it. The particles of matter are so small, they're small beyond our imagination. And we're not just talking, microscopic here. We are talking about a scale that is basically a whole different reality from ours. So let's recap. We've got these unbelievably tiny particles with spaces in between. But here's the next twist. They're not just sitting still. They're caught in this constant battle between two competing forces. On one hand, they're always moving, always jiggling around. But at the same time, they're pulling on each other, trying to stick together. And this constant dance, well, it defines literally everything. Right, so these particles are in constant, random motion, all the time. Ever smelled someone cooking dinner from another room? You're not actually smelling the big piece of chicken on the pan. What you're smelling are tiny, invisible particles that have escaped from the food, zoomed through the air, and literally danced their way right into your nose. This motion has a name. It's called kinetic energy. And the hotter something gets, the more kinetic energy its particles have, meaning they move way faster and travel farther. This whole process of particles just naturally mixing themselves up is called diffusion. It's exactly why if you put a single drop of ink in a glass of water, you can watch it slowly bloom and spread out. The ink particles and the water particles are all just jiggling and bouncing around, and they eventually get all mixed in. And just like we said, if you heat up that water, they jiggle faster, and that whole mixing process happens way, way quicker. But wait a second. If all these particles are constantly moving, why doesn't everything just fly apart? Well, that's where the other side of the battle comes in. There's a counterforce, a force of attraction that's always trying to pull the particles back together. The strength of that pull is what makes a solid, and a liquid. Think about it. Trying to break a piece of wood is tough, right? That's because the force holding its particles together is super, super strong. So this is the main event. The state of any kind of matter, whether it's a solid, a liquid, or a gas, it all comes down to this epic battle. The kinetic energy trying to push the particles apart versus that force of attraction trying to pull them together. Let's break it down. In a solid, that force of attraction totally wins. The particles are locked into a grid, just vibrating in place, held super tight. That's why a rock has a fixed shape and you can't really squish it. Now, in a liquid, it's more of a tie.
The particles have enough energy to slide past one another, but the attraction is still strong enough to keep them all together. That's why water takes the shape of its container, but still has a fixed volume. And then you have a gas. Here, kinetic energy wins by a landslide. The particles have so much energy, they completely break free and just fly around randomly, filling up whatever space they're in, and that's why gases are so easy to compress. There's tons of empty space to squeeze them into.
And we can watch this battle play out in real time just by changing a substance's state. Take ice, for example. As we add heat, we're giving its particles more energy, making them vibrate and shake like crazy. But here's something really weird. The temperature stays stuck at exactly 0 degrees Celsius until every last bit of ice has melted. The same thing happens when water boils. The temperature hits 100 degrees and just stays there. So if we keep adding heat, but the temperature isn't going up, where is all that energy going?
The answer has this cool name, latent heat. Latent just means hidden. See, when a substance is in the middle of changing its state, all that heat energy you're pumping in isn't being used to make the particles move faster. Nope, it's being used for one thing and one thing only, to break those forces of attraction that are holding them together. It's the hidden energy that fuels the transformation.
But things don't have to hit their boiling point to change state, right? I mean, a puddle on the sidewalk eventually disappears, even on a cool day, and your wet laundry will dry even in the shade. This happens because of a much slower, sneakier process, a kind of great escape for particles. So what's the difference? Well, boiling is what we call a bulk phenomenon. You're adding so much energy that particles all throughout the liquid can break free at once. It's a team effort. Evaporation, on the other hand, is a surface phenomenon. At any temperature, there are always a few high-energy particles right at the surface that just happen to get lucky. They have just enough of a kick to break free from their neighbors and escape into the air. And this explains why some things make stuff dry faster. If you spread your clothes out, you're increasing the surface area, which gives more particles a runway to escape from. A warm day gives more particles that escape level energy. And a windy day, that literally blows the escaped vapor particles away, clearing the air so more can follow. It's the perfect recipe for getting your laundry dry in no time. Now, this leads to a really cool effect, and I mean that literally. Evaporation causes cooling. Think about it. If it's the fastest, hottest particles that are escaping, then the ones left behind have a lower average energy. The surface actually gets colder. And this is exactly how sweating works. It's your body's built-in air conditioning system. Which brings us full circle to a final practical question that ties all of this together. So why should we wear cotton clothes in the summer? Well, we sweat to stay cool, right? And cotton is fantastic at absorbing water. It pulls that sweat off our skin, spreads it out over a huge surface area, and exposes it to the air. This maximizes evaporation. And as those particles escape, they take our body heat with them, leaving us feeling cooler. It's a perfect reminder that even something as simple as choosing a t-shirt is all about that invisible, chaotic, and totally amazing dance of particles that makes up our entire world.